Okay, here we go with the second part of our chemical equilibrium notes. This time we're going to talk about the reaction quotient and then predicting which way reactions would shift based on different additions or subtractions to help them maintain equilibrium. We're also going to talk about some of the more complicated, problems that might come your way. So we talked about the KEQ equilibrium expression. Q is basically the same thing, except that in this case, this system is not in equilibrium. And so you just substitute your initial concentrations of reactants and products into the equilibrium expression. And the point of this is just to see which way this reaction is going to be going, or is going. So in this case, if Q is a lot less than K, that means there must be a lot more reactants. And so this means that the equilibrium is going to have to shift to the right. So remember, if K is really small, that means you've got a lot of reactants, right? Because that's your bottom number on your Q and your K expression, because it's products over reactants, so it's very small. So again, if you've got too much reactant, so that's going to make your equilibrium is going to go to the right. It's going to shift to the right towards the product side to try to use some of that up to get us back to equilibrium. If they're equal, then the system is in equilibrium, obviously. And then if Q is greater than K, the opposite of our first case is true. We've got too much product. We've got a very large K, so our numerator is very large. And so now equilibrium is going to shift to the left to go back towards products, to use up some of those, go back towards reactants, use up some of those products and go back towards reactants. So here's an example. At 448, the equilibrium constant, Kc, for the reaction H2 plus I2 yields 2HI reversible is 50.5. Predict in which direction the reaction is going to proceed if we start with these amounts. So we have this many moles, 2.0 times 10 to the negative second moles of HI, that much H2 and this much I2 in a 2-liter container. Okay, well, we need to get our initial concentrations, which actually isn't all that hard to find because we have our moles, we have our liters, concentration is moles per liter, so 2.0 times 10 to the negative second divided by 2 liters is 1 times 10 to the second molarity. So same idea, same math, you get 5 times 10 to the negative 3 and 1.5 times 10 to the negative 2. So if this is our reaction quotient, HI squared over concentration H2, concentration HI, plug those in and we get 1.3. Well, what does that mean? Well, that is much, much less than our K, right? So that means equilibrium is going to go to the left. It's going to favor the products. So I'm sorry, it's going to favor the reactants. Another example, very popular process, the Haber process, we're going to talk about a little bit later. N2 plus 3H2 yields 2NH3. And we've got our Kp, so we're talking about pressures now because we have gases, 1.45 times 10 to the negative fifth at 500 degrees Celsius. In an equilibrium mixture of the three gases, the partial pressure of H2 is 0.928 atmospheres and N2 is 0.432 atmospheres. What is the partial pressure of ammonia in this equilibrium mixture? So what are we going to do here? We're going to set up our favorite thing, our ice table. So we know the equilibrium pressures of most of the reactants, but we need to get the product pressure. But we can still solve this with some variables. So we have our expression, right? Kp is the pressure of NH3 squared over pressure of NH2 times the pressure of pressure of H2 cubed. This guy we don't know. That's x. We don't know this. So this is x squared over 0.432 times 0.928 cubed. And we know all this is equal to our Kp, 1.45 times negative the fifth from the problem. So we need to solve for x squared. So x squared is just 1.45 times 10 to the negative fifth times 0.432 times 0.928 cubed. So x squared is 5.01 times 10 to the negative 6. Take the square root of both sides, and we get 2.24 times 10 to the negative 3 atmospheres. So that's our concentration of P and H3. Another example, this one a little bit more complicated. You've got a 1 liter flask filled with 1.000 moles of H2 and 2.000 moles of I2, again at 448. And the value of our reaction, our Kc of our reaction is 50.5. Right? What are the equilibrium concentrations of all the substances in moles per liter? So what are we going to do? We're going to do our ice chart. Okay, so we've got, initially we know how much we have. Okay, we have 1 molar H2, 1 molar I2, and we have 0 H2. I'm sorry, 0 HI. So how much does it change? Well, that's what we don't really know, right? Because in our previous example from last time, we were given an equilibrium concentration. This time we don't have an equilibrium concentration. So all we know is the stoichiometric ratios. So we know that this has gone up by 2x, and these have each have gone down by 1x, okay? Which means our equilibrium concentration is 1 minus x, 2 minus x, and this is just 2x. So we have, here's our equation, here's our equilibrium expression, Kc equals concentration of HI squared, H2 over I times I2. And so just plug everything in that we have. Right? Concentration of HI at equilibrium is 2x. We're going to square that. 1 minus x, 2 minus x equals 50.5. So if you've got a calculator that can do this, you can just plug this into your calculator and solve it, which is nice. But if you don't, you're going to have to expand to do the quadratic equation on this guy. So if we expand everything out, 4x squared, 50.5, distribute, and then rewrite it in our quadratic formula, so setting everything equal to 0. And now we can plug this into the quadratic formula. So x equals negative, actually it should be negative 1.515 all over this. And you get your two answers, 2.32 or 0.935. So if we plug these in, our 0.935, all right, we get our concentration of H2 as 0.065 molar, as 1.065 molar, and 1.87 molar. Okay, that makes sense. If we were to use the 2.323, we would actually get some negative concentrations, and that doesn't make any sense. So we're just not going to use that number. So that's how you do that. A little bit of quadratic formula for you. All right, Le Chatelier's principle. You will guaranteed see something like this on the big old AP test. But if a system is at equilibrium and is disturbed by a change in the pressure, a change in the temperature, or a change in the concentration, the system will shift its equilibrium position to counteract that disturbance. Right? So for example, if we change the concentration of something, so we're at equilibrium, this is how much H2 we have, NH3, H2, everyone's cruising along on a flat line, remaining constant. If we were to add some reactants, so here we spiked some H2, what's the system going to do? Well, it's going to try to use up some of that H2 by creating more NH3. So in the process, it also used up some N2, so combined some of that H2 with some N2 and created some NH3. So our new equilibrium has been established. We're trying to use up some of that extra stuff, so trying to counteract that disturbance. If we were to change the volume and or the pressure, if we increase the pressure somehow, we favor the reaction that's going to decrease the number of moles of the system, which would in effect reduce the pressure. Right? So if this is our initial volume here, we've got 2 moles of A and 1 mole of B. If we were to increase the volume, which would decrease the pressure, our reaction is going to go towards the reactants, because there's 2 moles over there. It's going to try to increase those to increase that pressure. And the vice versa is over here. Vice versa is true over here. If we decrease the volume, we're increasing the pressure. Now you can see the reaction is shifted all towards the B molecules because those are only 1 mole. So we're trying to reduce the pressure that way. And then a change in temperature, this one can be a little bit more tricky. Now you treat energy as if it's a product if our reaction is exothermic, right? Because exothermic means heat exits the reaction. Or if it's an endothermic, we have to add heat. So in this case, energy is a reactant. And so we just think of it that way. So at equilibrium, all right, this chemical, it's a complex ion with cobalt, is nice and blue, right? And this is an endothermic reaction. If we add heat, right, so in this case it's like it's a reactant, it's going to stay blue, right? It increases its blue really. But if we go the other way, we cool it off, reaction's going to shift the other side, right? We're cooling it off, we're taking away heat. Heat was like a reactant. If you were to take away a reactant, the reactant's going to shift to the left. This shifted to the left and made a pink solution. So a quick summary of those. This is mostly for your benefit. It's relatively straightforward. The hardest thing is here. If you just have to figure out if the reaction is endothermic or exothermic. So I talked to you before about the Haber process. AP board likes to use this as an example because it's a great example of equilibrium use and energy. This is basically we take nitrogen and hydrogen and turn them into ammonia, which is really good for agriculture because we use that for fertilizers. And what we see here is the percent of NH3 increases as you increase pressure and as you increase temperature. So you want a reaction that has a lot of pressure and a lot of temperature, or high temperature, and that's when you're going to get the greatest percentage of increase of NH3. All right, if we add H2 to the system, the N2 is going to be consumed, and those guys are both going to react to form more NH3. And this whole system helps to sort of drive that equilibrium by removing the NH3. So if you take that away, we're removing a product, and we're keeping that reaction shifted towards the product side, so the reaction kind of keeps going. So if we look at this, incoming, we've got our N2 and our H2. They come in here, and they get heated up, because we said it works best at a heat. So as they move up through this heating coil, they pass over a catalyst. We form a whole bunch of NH3, which is what we really want. We take away some of that heat, and we've got all of our hot gases with everything in there, NH3, H2, and N2, because not all of it reacted. Come down here, and we're going to recollect our N2 and our H2, and we're going to take our NH3 out. So by removing that, we keep our concentrations of reactants way high and our concentrations of products way low, and allow that reaction to keep happening. If we didn't pull this off, we would just build up so much, we'd build up NH3, and eventually the reaction would come to equilibrium. It wouldn't be able to keep producing the NH3. We'd have to take everything out and start over again. But by drawing off just that part, we can keep this reaction going and becoming a lot more efficient and getting a lot more ammonia, which is good for agriculture. So just some examples of figuring out which way equilibriums are going to be going. So here we've got our reaction, N2O4 can decompose into two NO2s, and our delta H is positive, so it means it's an endothermic reaction. We have to put heat in. So what direction will the equilibrium shift when we do each of the following? If we add N2O4, well, we're adding reactants. So that means we have a surplus of reactants, and then the system's going to work to get rid of that surplus, so the reaction is going to shift towards the right and use up some of that N2O4 and create more NO2. Vice versa, if we remove NO2, now we've got a dearth of products, so we're going to try to create more products, so the equilibrium is going to shift to the right. The pressure is increased by adding N2. What do you think would happen here? Well, in this case, is N2 part of our reaction? No. So that's not going to do anything. It's not part of this reaction. It's going to increase the overall pressure, but it's going to increase the overall pressure on everybody, so it's basically equal. What if we increase the volume? Well, if we increase the volume, that means our pressure goes down. So the system is going to try to increase the pressure. How's it going to do that? It's going to shift it to equilibrium to the right to produce more moles of the two NO2s as opposed to the one N2O4, which would increase the pressure. I should say increase pressure. Now, what if we decrease the temperature? Again, this is an endothermic reaction, right? So heat is a reactant. So we're decreasing that. We're taking away reactants. So the equilibrium is going to go to the left to try to generate some more heat. So that's how you can logic those out. Finally, talking about catalysts. We talked about those the unit before, something that increases the rate of a reaction. That's what we talked about last time. It's just important to know that it increases the rate of the forward and the reverse reactions. So they're both going to become faster. And if you use a catalyst, you do achieve equilibrium faster, but the overall equilibrium expression, the concentrations, those don't change. You just get there faster. So it doesn't really change the equilibrium expression. It just changes how fast it gets there. And that is that.